Alright, in this lesson, we want to Newton's laws of motion. There are three laws of motion that Newton's came up with. The first one, as you're seeing on the screen, it says that Newton's first law states that every object continues in a state of rest or of uniform motion in a straight line unless acted on by an external force. What this is just saying is that if you have an object, that object will remain at rest unless some external force is acted on it. So just like with a footballer right here, right? The ball is sitting on the field, and by applying a kick force to that ball will now change its position, obviously, or it will come out of that state of rest. Now, as the ball is traveling through the air, it will attain some type of constant speed. So that's where we talk about uniform motion in a straight line. Now, as the ball collides itself with the goal, right? That's another external force that is now acting on it. So that is what Newton's first law speaks to. It's just having objects either at rest, and it will remain at rest, or in constant motion, right? If there is, unless rather, there's some external force that is acted on it, all right? Now, Newton's second law is one that we have come across already, where it says that Newton's second law is equal to mass times acceleration. Now, there's a way how we can look at Newton's second law from another standpoint, and it's going to be related to momentum, the concept of momentum. Now, that's really where it has come from. That's really what Newton's second law is really based on the concept of momentum. Now, before we talk about that, let's just recall that momentum is the mass of an object times its velocity, and we generally use the symbol P when we're talking about momentum. All right. Now, according to Newton's law, it says that the net force applied on a mass m is directly proportional to the rate of change of momentum of the mass, and is in the same direction as the change in momentum. Now, because we're talking about change in momentum, right, and we're talking about it in regards to time, we can come up with that equation. So if you're dealing with momentum, right, you will have obviously you'll have an initial momentum, and you're going to have a final momentum. By way of subtracting the two, you can get a change in the momentum. So let's imagine that the object is at rest. When the object started moving off, right, the object being at rest would have a zero velocity. When the object reaches to some point, it will have some other velocity, right? So the change right there divided by the time can give us the actual force. Now, how we know that this is equal to mass times acceleration? If we go ahead and factor out the masses, and we're talking about this equation right here. If I factor out mass based on this equation, right, the mass won't change during the change of momentum. It won't change. What will change is just the velocity. And by way of looking at this, anytime we're dealing with the rate of change of velocity over time, we get acceleration. So that's how we pretty much derive that force is equal to mass times acceleration. It's coming from the concept of change in momentum. Good? So just factor out in the mass, and then realizing that change in momentum or change in velocity over time is acceleration. So that's how we were able to say that for Newton's second law, force is equal to mass times acceleration. Okay? So just remember that it's coming from the concept of change, the rate of change of momentum. So if you ever come across Newton's second law, you should remember that it speaks to the rate of change of momentum, right, on a particular mass or object. Now, this is just a breakdown of what we just said, right? So imagine that an airplane is in the air at some time 0 or time t naught, right? And at time 1 it has some other velocity and some other time. We could have found the change in momentum, right? And obviously dividing that by the time would gives us the force that the plane actually has. Now Newton's third law speaks to that if object A exerts a force on object B, right? It says then object B will exert an equal and opposite force on object A. And this is like a reaction kind of thing, where if I exert a force on something, that thing is going to exert equal and opposite force to me. So let's imagine that we have a book on a table, right? So the book sitting on the table, the force that would generally act downwards is the weight, right? And weight we know is equal to mass times gravity constant. Now the surface area here is going to exert an equal and opposite force, right? So if it's equal and opposite, then it means it's going to go upward. This force is known as the normal reaction force, and it is a force that comes as a result of the surface. All right, so the object has to be sitting on a surface, has to be in some contact with a surface before this can happen. Now mind you that you can't involve Newton's third law with more than one objects, or more than two objects I should say. It has to be two things. It has to be the object acting down and the surface that is giving the normal reaction force. All right, information is here for you to read that speaks to the normal contact force or normal reaction force. All right, so just remember that in the event of this case, right, where we have an object sitting stationary on a surface, that surface is going to exert an equal and opposite force to it. All right, now as regards to forces, now we have to get adapted to drawing what we call free body diagrams, and what these really constitute of is just an object, so to speak. In this case we're using a box to represent the thing that is in motion or whatsoever the forces are acting on. Now what you would do is look at that object and see what would be the force. So if the book is sitting on the table, right, then obviously there will be two forces acting if the book is sitting on the table. Now if the book is being pushed on the table or the box being pushed on the table, then we have other forces that are coming into play. Now in this event, let's look at this one. So we have obviously the normal reaction force going up like this, right? And it has the same magnitude as the weight. Because if the weight is 147 newtons, the normal reaction force must be the same. Now by way of applying a force to the right of 60 newtons, then there is going to be what we call a frictional force that is trying to oppose the motion of the applied force. All right, so you would go ahead and put in your arrows, similar to what this is saying right here, and you will see us utilizing this type of concept some more when we move on. All right, but this is just what we call a free body diagram, and it is just one that you use to identify the different forces that are acting on the object. All right, and of course, because force is a vector, we use arrows to show where it's going. Okay, now there's something important, because we're going to come across inclined planes and objects sitting on an inclined plane. One of the things that we have to note and remember is that the weight of an object, irrespective of the position it is in, the weight is always acting vertically downwards. All right, no matter what. So imagine that this box is right here, right, and it is on this inclined plane. Now this box, cool, is going to have a weight associated with it. Now the weight is going to act vertically downwards. No matter what the situation is, the weight always acts vertically downwards, and that is mainly because of the pull of gravity, right? Unless Until we don't have any proof to say that it doesn't act down directly, then we're going to stick with what this is. Now, whenever you have this type of situation, right, and we want to see the forces that are acting, we have to take into account resolving the weight force, because the object is on an incline, right? It is hard for us to add the forces together and see the relationship between the normal reaction force and the downward force. So with that being said, we have to now resolve the weight of this box into its perpendicular components with respect to the inclined plane. So you're resolving with mg with respect to the incline, right? So let's look at it now. There's a thing that we must point out, that whenever we look at an incline problem of this nature, and we see an angle right here, right? This 35 degrees is going to be the same angle in between here, always. And this was proved from some mathematical laws of angles and all of that, right? But we don't really want to focus on that. What we want to do is to tell you that the angle that is formed between this section of the triangle right here, right, or of the incline, I should say, between the weight and the vertical component of the weight, right, that angle is going to be the same angle that is between the incline and the horizontal surface. Good. Now, because we're resolving this force, we have to resolve it in respect to the incline, right, because that weight is coming from the incline or coming from the surface of the incline. So we have to resolve it. By resolving it, one component is going to be here. This component is going to be mg sine. And as you can see, that's written here already, that this component right here is going to be mg cos 35. Why we say 35 is because we formed a right angle triangle at this very moment. Pretty much a right angle triangle. Now, by looking at our right angle triangle, the angle 35 is adjacent to this side. And if we want to find what the adjacent is equal to, the only trig ratio that we can use is cosine theta is equal to adjacent upon the hypotenuse. And we will take the hypotenuse and multiply it by cos theta. So we have, and in this case, our hypotenuse is mg. So mg cos theta is equal to the adjacent, and that's how we were able to rewrite this to say mg is equal to cos 35. Okay? Similarly, because this side is the opposite, okay? This side is the opposite. When we resolve the components, this is why this became mg sine 35. Alright? So that's just resolving the vectors into their horizontal and vertical component. So with this being said now, what you guys will understand or see is that because the normal reaction force is a force that is opposite to the downward force that acts directly downwards, we can realize that the normal reaction force is equal to mg cos 35. Alright? Now, let's kind of move away a little bit from that, and we're going to kind of focus our attention a little bit on Newton's laws of motion being applied in some other cases. Now, what you're looking at right now is what we call an Atwood machine, right? And an Atwood machine is just like a pulley, right? So, if you have ever gone on a construction site and you need an object to go up in the air, right? Quite often you will realize that they use a pulley to help bring objects up in the air. Alright? And somebody would have to apply some type of force on one end of the string to bring the object upwards. In elevators, this thing is also common, right? There are many applications of an Atwood machine, or we call it a simple pulley. Now, whenever you have this type of Atwood machine, we refer to it as a full Atwood machine, right? And all it is having two masses being of different weight or different mass, being attached to the ends of the pulley, right? Of some type of rope. When you have that situation, quite often we will want to find what would be the acceleration of the entire system, because what you'll understand, guys, is that because you have one object having more mass than another object, the one side is going to pull down to the earth, right? Obviously, because you have the weight overcoming the object being going downwards. So in this event, if we're looking at object A or figure A, big M would have the upper end in terms of the forces, right? So it means that the acceleration for this Atwood machine is going to be on this side. It's going to be on this side. Now, whenever we're associated downwards, or whenever we're talking about vectors on a whole or acceleration, if you're going downwards, then that is basically saying you're going in a negative direction. So in this event, our acceleration is going to be negative because it's going downwards. Okay? Now, there is a formula that we can derive whenever we want to find the acceleration of the Atwood machine problem. And what you would realize us doing is that we have to look at these objects by themselves. So everybody and put in the forces that are acting. All right. So if we're taking object big M, right? So for big M, the net forces that are acting on this system is going to be as of such. Now, because the tension force is acting upwards, we associate upwards as being positive, right? So we would write that as our positive force. So if we're saying net force is equal to mass times acceleration, our net force is going to be our tension force minus mg, and this is equal to negative m times a. Why I say negative is because big M is the one that is going to bring the system downwards, and that acceleration is actually negative at that point. Now for small m, we can also find the net force. Net force is equal to m times a. Now, the forces associated with this system here is the tension force and the weight of that particular object. Because the tension force is acting upwards, we associate that as our positive. So we'll say that Ft minus mg, because mg is acting down, we treat that as positive, as negative rather, and this is equal to m times a. Now, in order for us to find the equation, we have to subtract this equation. So we call this equation 1, and we call this equation 2. We have to do a subtraction. When we do subtract both equations, we're basically going to eliminate something. So, by way of subtracting, this is what we're getting. So, Ft minus mg is equal to minus mg times a. My God, what did I say a while ago? Ft minus mg is equal to minus m times a. Good. And we're subtracting Ft minus mg is equal to ma. So let's go ahead and subtract. And we're subtracting everything. So Ft minus Ft, that gives you 0. Now minus mg minus small m times g, that becomes positive mg, And this is equal to minus big M times A minus MA. Let's do something now. Let's kind of group these things and factor out a few things. So if we're grouping G's by themselves, right, this is what we would get. So G times negative M plus small m is equal to, let's factor out negative a. So negative a on this side is equal to m plus small m, big M plus small m. Now we want acceleration, so we'd have to divide. Before we do that, let's divide both sides by negative 1. If we're dividing both sides by negative 1, then we're going to have a different thing happening here. What you would have is G times M minus M minus small m, right, equal to A times M plus small m. Then all I would just need to do next is to divide rather both sides by big M plus small m. So our acceleration for a full Atwood machine is nothing more than saying acceleration is equal to gravity times the big M, which is the larger mass, minus the smaller mass, divided by the sum of the masses. So this is the equation you would use if you want to ever find the acceleration of the entire system, right? As the object, as big M pulls the object downwards. Now we have another aspect of Atwood machines, what we call a half Atwood machine. And whenever you have a half Atwood machine, this is what is taking place right here. Now, because M2, we're going to treat M2 as the larger force, right? What we would have to do in this case is to look at what are the forces that are acting on the system. So if we're looking at M1, at M1, right, the only force that is acting is the tension force, which is acting like this. It's pulling the object to the right. Then clearly we can see that if we're looking at M2, there's going to be a tension force that is acting upwards, so Ft, and you know there's a weight that is acting downwards, which is Mg. All right, now let's look at the net forces acting on M1. So net force for M1 is equal, because there's only one force acting at this very point along the horizontal, then we would say that Ft, which stands for our frictional force, tension force I must say, is equal to M1 times the acceleration. Because the object is accelerating towards the positive side, right? Because going to the right is we treat that as positive. So in this event, our acceleration is going to be positive. Now, as the object reaches the pulley, right, you realize that M2 is pulling the object down. In that event, we now realize that that Mg is obviously the greater force. So if it's the greater force, it means that when I'm finding the net force, so F net is equal to mass 2 times its acceleration. Good. Now let's write out the net force. So M2G minus Ft, this is because the weight of the object is pulling the object down. And we multiply this now by the mass times the acceleration. You might be wondering why is it that the acceleration is not negative? But because we already associated a direction with the acceleration from m1, because m1 was going in the positive direction, it means that the acceleration at that point would have been positive. So when it reaches this point, it is still actually positive. Alright? So by way of doing this, we can equate the two things together. Because we know that ft is equal to m1 times a, we can substitute that in one of our equation right here. So we can say sub ft equal m1 times a into this equation. So if we go ahead and do that, we have m2g minus m1 times a is equal to m2 times a. Let's group things together. Want a by themselves and g by themselves. So we have m2g is equal to m2a, and that is adding to m1 times a. We can factor out the a on this side. So if we factor out the a, we have m2 plus m1, and that is equal to m2 times g. We want a by itself, which therefore means that a is now equal to m2 times g divided by m2 plus m1. So that's what you would do if you ever get a problem like this. You would just use this formula here, or you just take it from all of what we did a while ago regarding the tension force, equating them, substituting, and coming down all to that equation that says a is equal to m2 times g divided by m2 plus m1. Alright, now there are other scenarios of the incline plane situation. This now is still an Atwood machine per se, but it now involves an inclined plane, so to speak. Now whenever you have this inclined plane, you're focused on the forces that are acting along the incline. So you don't have to put in the normal reaction force. We know that the weight is acting vertically downwards, and the weight is equal to mg. We know that there's going to be this horizontal component of the weight, and this is equal to w, or not w, but we can say mg sine theta. Good. And clearly on this system, if we're supposed to join the forces, there would have been a tension force ft on this object big M. There's also the weight of this object acting on this side. There's also the tension force acting as well. So we could treat our free body diagrams as such if we want to, because big M is the larger object. We expect that this is the way it's going to accelerate, and we are trying to come up with that formula for the acceleration. So in order for us to do this, we would look at big M and see what are the net forces that are acting. So what are the net forces? Because it's acting downwards, well, in the sense where M2, not M2 I should say, in the sense that mg sine theta, that is the force that is of greater magnitude, because the object is pushing down in that regards, that direction. So this tells us that our net force is equal to mg sine theta minus the ft, which is the tension force. This is equal to negative big M times the acceleration. Object is accelerating downwards like this, so it tells us that that the acceleration is negative. All right. Yeah. So it tells you that acceleration is negative. Now, okay. Now let's see if we can talk about this some more. So we looked at that particular object. Let's look at small m. So for small m, we now realize that the net force, because this small object is accelerating upwards like this, right? We can say that Ft is the force with greater magnitude. So if we're trying to find the sum of this, we have to subtract Ft from mg, or mg from Ft. And this is equal to small m times the acceleration. The object is accelerating upwards, so then it's a positive acceleration. So by way of looking at this, we have this equation here. We can make Ft the subject. Let me just see right here. Yeah. So by making Ft the subject, this is what we have. Ft is equal to plus mg, right? And that's when we make Ft become the subject. By way of doing this, we can now substitute Ft into this equation 1. So if we're doing that substitution, this is what we have. We have mg sine theta minus bracket mg plus mg, ma plus mg. My bad, sorry about that. And this is equal to minus ma. Now, with that being said, we can go ahead and expand this with the negative signs. If we go ahead and do that, we have mg sine theta minus ma. By the way, this is small m times a minus m times, wait, there might be something. Let me just check. Yes, it's correct. I think it's correct. Yeah, it's correct. It's correct. I don't know. I had something incorrect right here, so I know. 1 second. Yeah. So yes, this would have been a minus right here. Yeah. Now, this is all of this is equal to negative ma. Okay. So what we would do is to group like terms. So we'll group ma by themselves. I will group a's by themselves. I will group what we call it, g's by themselves. Alright, because g's are common on one side, a's are common on another side. You can put that together. So by way of doing that, we have mg sine theta, right, minus mg, and this is equal to negative big M, right, plus small m times a. Having said all of this, right, we can do a little bit more of a factoring. So if we factor out g, we have mg Well, we have g, factor out the g, and then we have m sine theta minus m, and then this is equal to, if we go ahead and factor out the negative a, we have m minus small m. And so if we go ahead and divide both sides by negative 1, we have this thing here to say that g is equal to, or g multiplied by m minus big M sine theta, that is equal to m minus big M, which tells us that our acceleration A is equal to g bracket m minus big M sine theta, and this is dividing. Okay, so just a quick correction, and let me just see if I can erase it. All right, so right here, when I no longer minus, so once I factor out the negative, this becomes positive right here. So this is the formula that we should have to say that the acceleration is equal to g bracket m minus big M sine theta close bracket divided by big M plus M. So this is the acceleration formula, right, that you would use whenever you want to find the acceleration down an incline, right, with the fact that there is no kinetic frictional forces acting. All right, now let's see if we can put a little bit of this to practice. Now this question is for you to try, right? Now, so that would be your homework question. I'll try the other one that's coming up next, this one. Now, in the event that we have that particular question, having this question, it means that we would use, this is a full Atwood type of question, so you have to look at the question and see what exactly applies to you. So we know M1 in this case is equal to 6 kg, M2 is equal to 4.5 kg. You can pause the video and watch and read the question if you want, right? But what we're really trying to find is just the acceleration, and we're writing down what we know, so we don't know the acceleration. Obviously we don't know that, so we can just go straight to the equation that we would have derived just now. If you get the question and you don't know how to give, if you don't remember the formula, right, then you would have to take it from where we derived the formula from, right, to find what the acceleration is. And that is not hard by just looking at the forces, because in this event M2 would be the greater object, so we expect that the acceleration is going to be negative, and that the forces here is going to be the tension force and the weight mg acting down. For this as well, mg acting down, tension force acting upwards, right? And you do your substitution, you're not substitution, but equating the things are what I should say, subtracting them and all of that to find the thing. All right, now here we have the equation to say that mg, not mg, a is equal to g times big M minus little m divided by m plus small m. We can put in the values. We know g, which is the gravity constant, which is 9.8 and this is multiplying by the difference in the mass. That's going to be 1.5, and when we sum the masses we get 6.5, not 6.5, my bad, 10.5. So by way of working out all of this, we should get an acceleration of 1.4 meters per second square. So that covers that part of the question. Now, similar question, different masses. So all they want you to do in this case is to find the tension force. What you could start off with is by using the acceleration formula to say A is equal to G times M, big M times small m divided by M plus big M. Good? Now, with this being said, we can go ahead and find acceleration. Putting in all the values, 9.8, right? Find it, let's subtract 24.5 from 20, right? Divide by 20.5 plus 20. Should be getting some stuff as to say 44.1 divided by 44.5. All this is equal to the acceleration. So at the end of the day, when you get the acceleration, that should be supposed to be 0.99 meters per second. Now, in regards to the tension force, we can use any one of these equations because we know that the net force is either equal to Ft minus mg times the acceleration. If we make Ft becomes the subject, we can find the tension force, and in this case m1 times A plus m1 times G. M1, we can factor out M1, so M1 bracket A plus G. So we know A a while ago, we know M1. M1 in this case is 20. 20 times the sum of the acceleration, 0.99 plus 9.8. This would tell you the, where's the calculator. At the end of the day, the tension force Ft has a value of 215.8 newtons. Alright, so that's what you would have done in this event. Now there are other questions. Use the formula, guys, and see if you can solve this problem. Alright, so I'm going to next it so you can see the other problem if there is any. So I think that's about it regarding this aspect of the using Newton's second law mainly, because as we can see, if we're talking about acceleration, then obviously Newton's second law would come into play. Okay, so that's about it for this particular lesson. Apply what you have learned, and we will more as we go along.